Okay. So for hybridization, this orbital stuff we've been talking about, like, oh, the electrons reside in the s orbital or the p orbital or the d orbital. That's not really true experimentally. So experimentally, when you have an atom that's forming bonds with other atoms, the electrons take a less energy level. They take a lower energy level than if they were just by themselves. And that makes sense, right? Because why would an atom bond to another atom if it wasn't energetically favorable for the atom to do that? So that's why, like, carbon dioxide, very stable molecule. It's an inert gas for the most. Well, yeah, it's pretty inert. So it's much more stable than carbon or oxygen by itself. And that's because of hybridization. So these electrons, and this is a good way of representing it. So carbon, we all know, has 4 valence electrons. The valence electrons of carbon, they reside in the ground state. There's 2 of them in 2s, and there's 2 of them in 2p, right? 4 valence electrons, you have 2s1, 2s2, 2p1, 2p2. But when they bond, when they form bonds with other atoms, they are represented by hybridized orbitals. So that's what these are. So they're of a generally lower energy level, even though it's kind of like an intermediate energy level, but it's kind of like an energy medium, right? It's in the middle. So and then the electrons are kind of like spread out to where each single electron could accept a pair, can accept another one. So, and this is called an sp3 hybridization. So carbon goes through sp3 hybridization when it forms 4 separate bonds. And that's because the electrons kind of disperse into these hybridized orbitals to make it more energetically stable. So if that's a little bit complicated, don't really worry about the concept of that as much. Just be able to understand, once we go over examples, how to determine what is sp hybridized, sp2, sp3, dsp3, d2, sp3. So that's like the main enchilada for hybridization. So we'll go back and look at that. So yeah, here's methane, right? So you'd expect, because you have hydrogen and carbon, carbon's molecular orbital diagram, that's right here, you have, just like we saw before, 2s2 and then 2p2. So you think, oh, it could easily accept electrons here and here. Can you see my cursor, by the way?
Yeah.
Okay, cool. So you could see, it can accept electrons here and here, and only 2. But that's not true because of hybridization. And like we saw, you'd have 4 separate hybridized orbitals. You'd have sp3, so then it can actually accept 4 hydrogens, which would then be the observed reality right here. And then you'd have a tetrahedral methane molecule that we learned about. So there are 5 types of hybridizations. So there's
Can you go back for a second?
Yes.
Sorry. So, like, what's really the difference between those 2 pictures?
Right. So theoretically, based on the molecular orbital diagram of carbon by itself, you would think that carbon can only accept 2 bonds. And that's why there's 2 hydrogens here.
But we know that carbon accepts 4.
Exactly. And the reason why we know, and the way we can represent that is by hybridization. So it's weird how the scientists came up with this, because we knew that methane existed before we knew about hybridization. Right. So we kind of had to hypothesize why is carbon taking 4 bonds if the valence molecular orbitals look like this, where it can only take 2. So they're kind of like, oh, maybe it's some weird, like they did some like quantum. This is all like quantum mechanics of electrons. So it's supposed to be difficult. It's not supposed to be easy to understand. I don't understand it fully. It's really tough to understand, to explain also. So,
I feel like wait, Professor, is it kind of similar to like, I forget exactly how it went, but like when you reach the 6th and the 11th, maybe, or the 5th and the 11th, right? For the balanced electron thing,
the 4th and the 9th.
Yeah, the 4th and the 9th. Right.
Yeah, so it kind of like you take 1 electron from 4s and put it here.
Yeah.
Yeah, kind of same thing. So this is the same kind of concept, but what's happening, if you go back to the other diagram, so this 2s electron, the second one, is going to the other 2p. And what that's doing is you kind of, with that new energy level, you kind of, that makes the molecule more stable, doing it that way. And that kind of brings the top 3 orbitals that were at a higher energy level, or subshells, and brings them down and kind of makes an average of all of them, otherwise known as hybridizing. So it hybridizes those orbitals, and it makes them on the same energy level, whereas an S is obviously lower energy than a P.
Yeah.
So yeah, it's a good concept. So yeah, that's what happens, and that's how you know it can bond that way. So going into the different types.
I have one more question.
Oh yeah, go for it.
How many things do we look at that we don't even know are like hybridizations?
Everything. So every covalent bond is hybridized. We just didn't learn that yet. Yeah. Yeah, so bonding is actually really complicated. We learn it first as like covalent ionic. Oh, you just share the electron. But once you get into like electron quantum mechanics, it gets really complicated. We talked about probability distribution a little bit. We talked about the shapes, and we talked about molecular orbital diagrams, where the electrons are, quantum numbers. But then it gets more difficult when you talk about hybridization. And then what we're going to talk about next is valence bond theory, which kind of tells you a little bit more about these bonded molecules. So hybridization, every electron involved, bonding or not bonding, in a covalent bond is hybridized, or in a covalent molecule is hybridized. So that's pretty.
I mean, but what if there's like, oh yeah, I guess that's not the same.
Yeah,
like, what about 2 heliums bonded together?
So that's a really good question. So we're going to talk about that exact example. So that's impossible, and we'll talk about why it is when we go to valence orbital theory, or valence bond theory. Yeah, there's too many of them. So yeah, that's a really good question you asked. So yeah, because they have 8 valence electrons. Like, how does that work? But it doesn't work. That's why you thought of it. So it's interesting. So okay. Good points. Now, for hybridization, the easiest way to understand it for your exam, just to not talk about concept, just talk about what you need to know, is these are the 5 hybridization states that any atom could have, except for hydrogen. Hydrogen cannot be hybridized. And also another thing, hybridizing, the way any bond occurs, any covalent bond, is by orbitals overlapping each other. So you have an s orbital and a s orbital from a hydrogen and a p orbital from a carbon, and they overlap to share electrons. And that's exactly what's happening. And that's how we call it a hybridized orbital. It kind of averages the energy between the s and the p, making it a hybrid orbital. So that's how any bonding occurs. So you have sp, sp2, sp3, sp3d, sp3d2. Now, the easiest way is to just know the number of letters is the number of electron groups. So I'll say that. The number of letters is the number of electron groups. What that means is, in sp, there's 2 letters. Therefore, 2 electron groups in the atom that you're talking about. sp2, there's 3 letters. Think about this 2 and the 3. Think about them as exponents. So sp2 is basically saying, wait, half of my, am I not right? Whatever. Think about, oh no, there it is. So think about sp2 as spp. That's 3 letters. Therefore, 3 electron groups. sp3, just like methane, is spp. So that's 4 electron groups. And then so forth with sp3d, sp3d2, you're going to have 6 electron groups here. So something like SF6 is going to be sp3d2 hybridized. because that's the number of letters there, and that's the number of electron groups attached to the central atom sulfur. So we're going to do some examples. That's the easiest way to understand hybridization. So here's an example. Now, hydrogen, you don't really consider it to have a hybridization because it only has one electron group on it at all times. So it's just kind of S. It's not really a hybridized orbital. It's just an S orbital. Then for carbon, you count the electron groups. 1, 2, 3, 4. Okay, 4 of them must be sp3 because S is 1, 3 Ps, and you have 4 separate hybridized orbitals. Then you have nitrogen right here. So nitrogen is also sp3 hybridized because you count the electron groups. So you have 1, 2, 3, 4. So now there's 4 electron groups again. Even though these are lone pairs, they still are in a hybrid orbital because if these electrons are bonding, then those orbitals have to be on the same playing field to make an sp3. So like if you have, better way of explaining it, where's that chart before? The energy chart. Yeah. So if you have the same thing for nitrogen, in nitrogen, only 3 of these are going to be bonding. Let's say these first 3. This one might have another electron, but it's not going to be bonding. That doesn't mean this changes, this subshell changes energy level. It's still the same hybridized orbital. It's just not bonded to anything. And that's totally okay. So the idea is that when you have any covalent bonding, the orbitals overlap to create hybrid orbitals for the entire atom, whether they're bonding or non-bonding electrons. So that's the key. Okay, any questions on how I got sp3 for both of these? We'll do more. No? Okay, going forward. Is methane sp3, ammonia sp3. Okay, so we're going to do more examples, but first, sigma and pi bonds. You can talk about this all day, and there's a lot of concepts that go into it, but basically, a sigma bond is a single bond, and a pi bond is anything additional, not a double bond, but anything additional to a single bond. So for example, if you have cyanide, right? C triple bond N. You're going to have one sigma bond, which is this one, sigma, and you're going to have 2 pi bonds. The pi bonds are going to be the additional bonds to the sigma. So in a triple bond, you have 2 pi bonds, 1 sigma bond. And sigma bonds are generally stronger than pi bonds based on the electron density. They have a higher electron density, and they're more along the axis. So here's how they're represented. Now here is a molecule of what is this? This is aldehyde, formaldehyde, or no, it's an aldehyde, the simplest aldehyde. So what happens is this is a sigma bond. It's the first bond, the first electron sharing, the first hybridized orbital that occurs between one of the atoms, carbon, and then the other one, oxygen. Then every additional bond is going to be a pi bond. So I mean, this pi bond is nothing here, but you're only going to have 1 pi bond here because there's a double bond in the structure. So you're only going to have 1 sigma and 1 pi. Why you need to know this information? Because it kind of helps you a little bit when we go over to valence bond theory, which is kind of complicated, but we'll try to simplify it. So any questions on what a sigma bond is and a pi bond? Sigma, single, pi, anything additional to single. Okay, so with this structure,
so could a pi bond be lone pairs?
So no, so sigma and pi bonds are only shared hybridized, well, they're all hybridized, but they're only shared electron pairs between 2 atoms. So they're only bonded electrons. So that's why we didn't, so there's 2 electrons here, or actually 6 of them. So yeah, we don't represent, or sorry, not 6, 4. I think they should both be there. Now they're not represented by any sigma or pi because they're not bonded. Only bonded electrons are. Okay.
What's P?
What's up?
What's P?
P.
Like
What?
P?
Where, up here?
Sure.
Oh, yes. So that's the hybridization. So that's the p orbital hybridization. So this means that there's the pi orbital or the p orbital from carbon, p orbital from oxygen, and they're overlapping. That's where those electrons are overlapping. So that's both of the p orbitals. And then you have an s orbital from carbon and an s orbital from carbon, a p orbital from oxygen, and they're kind of going together and hybridizing. So yeah, from this molecule, let's do the hybridization. So hybridization of carbon. Anybody want to tell me what it is? Well, it's right there, but so there's 3 electron groups. I'll just go over it. Well, no, there's 3. So there's 3 electron groups. Remember that an electron group could either be free valence electron pairs, a single bond, or any other bond. So there's 1, 2, 3.
Okay.
Yeah, so 1, 2, 3. So that means if it's 3, it's going to be sp2. Now for oxygen, you have 1, 2, 3. So it's also going to be sp2. Like that. Okay, cool. So don't worry about that. Don't worry about bond rotation, not important. Cis and trans, not too important right now. Here we go. So, well, is there any better examples? And so here's more sp2 hybridized molecules where you have, so this oxygen now is sp3. And the reason why, you have 1, 2, 3, 4. You have 4 electron groups, so sp3. This carbon is just like we saw before, sp2, and same with the oxygen is sp2. What else we got? sp. So sp is when you're going to have 2 electron groups attached. So a good example, like I said before, was this is hydrocyanic acid, but I use cyanide, where you're going to have an sp hybridization of carbon because there's only 2 electron groups. One of them is the single bond, the sigma bond here, and the other one is the triple bond, which contains 1 sigma bond in the middle and 2 pi bonds, one on either side. So this carbon is going to be sp hybridized because of that. There's 2 electron groups. Same with the nitrogen. The nitrogen is going to also be sp hybridized, but it's going to have one of those hybridized orbitals is going to be contained, or hybridized subshells is going to be contained with 2 valence electron pairs, or 2 valence electrons that are free, not bonded. And then the other one is going to be the triple bond. So it's also sp hybridized. And then hydrogen is just S because it doesn't have a hybridization. Okay, so let's do more. So yeah, you see the hybridized orbitals, how it occurs. Kind of same thing we went over before. Then you have sp3d. So we're just adding more bonds here. So you see this iodine, this weird molecule right there. Now all we could do is count up the electron groups. And yeah, you could remember it as, oh, it has a trigonal bipyramidal shape, or a seesaw, T-shaped, or it's linear with the lone pairs. That's too complicated to remember all those different things. Don't really worry about that when we're dealing with this hybridization. Just worry about the number of electron groups coming off of it. So in this case, you have 1, 2, 3, 4, 5. Therefore, sp3d. That's it. So any questions on that? It's the first bullet point. Atom with 5 areas of electrons around it. So 5 electron groups. And then you're going to have the last one, which is sp3d2. So a lawnmower? I think that's Nicole's thing. I'm going to mute Nicole. Sorry, Nicole. I heard a lawnmower in the background. I got to mow my lawn. I have like a very small lawn because I'm in a condo apartment thing in Jersey City. So it's like a 10-foot by 10-foot lawn. It's great. I know. So I can get scissors and cut it. But anyway, so here is your most bonded or most electron pairs hybridization orbital, where you have sp3d2, which means that you have 6 areas of electrons or 6 electron groups. And then don't worry about, oh, it could be all these shapes. Yeah, it definitely could be all those shapes, but let's worry about how many electron groups first. So you're going to have 1, 2, 3, 4, 5, and 6. So sp3d2. Okay, cool. So I think this should be, here we go. Here is a summary chart on all the different hybridizations. Now, is there any question on those? And then there's a better chart, the one I had first. Yeah, this one is just as good. So yeah, here's a good summary. I'm going to copy this and put it on the bottom. Like that. So yeah, that's a really good slide to go off of for hybridization. Oh, it's okay, Nicole, about the lawnmower. All right. Any questions? No? Okay. Now, here comes, oh, let's do this one first. Let's do hybridization practice. So the oxygen, let's count the electron groups. 1, 2, 3. So it must be sp2 hybridized. Nitrogen, 1, 2, 3. Must also be sp2 hybridized. Chlorine, 1, 2, 3, 4. Must be sp3 hybridized. That's it. Ta-da. Yep, there we go. And then what they mean by bonding scheme, really what that means is the length of the bonds, how it's going to be represented. And we know based on the size and the type of bond, what the bond length is going to be. Because bond length is inversely proportional to bond strength. So the shorter the bond, the stronger it is. And we know that double bonds are stronger than single bonds. Therefore, the oxygen and nitrogen are going to be close together in comparison to nitrogen and chlorine. Another representation, you could think, oh, chlorine's bigger than oxygen. And yeah, that's true. And that helps the bond length increase a little bit. But really, it's due to the number of bonds, single versus double. And triple is going to be a lot shorter than double is. Or actually not that much shorter, but it's going to be shorter by a good amount. So yeah, that's what they mean there. So everything we learned so far with Lewis structures and the shapes and the molecular orbitals, there's some problems with it. So basically you can't do 2 things. One of them is you can't predict the molecule's magnetic behavior perfectly. So we talked about paramagnetic and diamagnetic. So we talked about para as being if you have unpaired electrons. So if you have any one or more unpaired electrons, it's going to be paramagnetic. And then diamagnetic, put dimag, is going to be when you have all paired electrons. And our molecular orbital diagrams would have the like 1s with the box and then the 2p with the boxes, like these, they couldn't perfectly represent whether a molecule was para or diamagnetic. So for example, O2. So O2 has 6 valence electrons, or oxygen has 6 valence electrons, and you have O2, you're going to have 6 more. So it's going to work like, how would it even be represented? So let's see. So you have, wait, so we'll just do O. So O2 is like that. And what you have is I'm not going to draw the orbital diagram, but it will be, where is it? I'm going to show it. I have a thing. Where is it? Here we go. So O2 is paramagnetic, but the Lewis structure actually shows it as diamagnetic, that it has everything is paired. But when we learn about this, we'll see that it's not. But let's get into it one step at a time. All right, so that's one thing that the molecular orbital theory, the reason why it's important, I think I called it something different. So this is the new thing. This new thing I'm going to learn is molecular orbital theory. It's a little bit different than valence bond theory. Valence bond theory is Lewis structures with the molecular orbital diagram, not molecular orbital theory. There's a lot of different crap. But basically, this one is taking more of a quantum approach by applying Schrodinger's wave equation. And we're not going to learn in depth about any of that. It's applying these calculations to molecular orbitals and representing them in a different way. So keep in mind, all of this is representing things that we can't understand. So if it's difficult and you're like, why the hell is that the case? Sometimes it just is. And that's one thing I learned about teaching this class. And that's why I hate teaching this stuff, because I hate when you can only find a limit to explaining something without getting crazy. So sometimes things just are. So don't worry about that too much. So basically, well, okay, so this is worth mentioning. Sometimes, well, wait, I didn't cover something. So, okay, there's two things. I forgot the second thing. There's two things that this molecular orbital theory can predict. One of them is the exact magnetic behavior, whether it's para or di, of any molecule that the Lewis structures can't. The second thing is it can actually predict if a molecule is able to bond. Such as what, who was saying that before? Was it Jabral? You were saying about the helium-2?
Yeah.
Yeah. So helium-2 is an example that you probably saw when I was flipping through the slides. And we're going to cover that one. Is it possible is it a viable molecule? And this molecular orbital theory will actually tell us that. So it's a pretty powerful technique. So before that, once you combine, so there's wave equations. So there's Schrodinger's wave equations. We've seen waves before, right? And remember that there's two types of interference. There's constructive and destructive interference. So if you add both of these waves together, it would make constructive interference, meaning they will just add together and the waves will have a higher amplitude or higher intensity. Then there is destructive interference. So if you have these two waves add together, they will add to 0. And that'll be the addition of them. So these two interferences have their place in molecular orbital theories. Now, when you have these wave functions of different electrons, they can either combine constructively or destructively. So we'll skip this and then we'll talk about this. When you have constructive interference, that means you have bonding molecular orbitals. That's a good thing because the electrons it's just easier to bond and it's lower energy when you have constructive interference. Why? Because of quantum physics. But they determined that it's lower energy and the atoms are more happy when you have constructive interference of electron waves. That would make the bond occur. Therefore, you're going to have this orbital called bonding molecular orbital. So there's going to be different types of orbitals here, bonding molecular orbital. Then, when you have destructive interference, that is not favorable, and that requires more energy to have destructive interference molecules go close together. And I guess that makes sense, kind of, because they wouldn't add well, right? They would bond weird, and they wouldn't bond at all. So what we call them is sigma star. This is sigma, meaning this is just a single bond represented, and this is 1s. So this is the 1s orbital. And sigma star What that means when you have a star is that's the anti-bonding molecular orbital, meaning it's the representation of the destructive interference of Schrodinger waves of two electrons that want to bond together, but they can't because of energetically not favorable interaction. So this is what we represent, an anti-bonding orbital. So what the other equation, what this slide was, is that bonding orbitals have lower energy and they're more favorable. Anti-bonding, higher energy, less favorable. That's the only thing that's important. So anti-bonding, less favorable. Bonding, more favorable. And there's an easy way to understand that is, before we go over bond order, this is how we're going to represent these bonding and anti-bonding orbitals. So there's some stuff going on here. Let's represent it. Let's understand it. Here is the dihydrogen atom or molecule, H2. H2 has two hydrogens in it, right? This is hydrogen number 1. This is hydrogen number 2. Or I'll put 2 there. Well, actually, no. Yeah, I'll put 2 there. Hydrogen 1, hydrogen 2. Now, hydrogen in general is just 1s1, right? That's the only electron. So if you take two 1s1s, that's where you put them on the side here. Then when they bond, they are only taking place in a sigma bond. There's no pi bonds in anywhere in a hydrogen 2 molecule. So what happens is when they bond, each electron from hydrogen will bond perfectly, bond well, and it'll create one sigma bond. And there'll be no electrons in the sigma star orbital. Why? Because when things bond, they like to take the energetically favorable route when possible. So that makes sense. If you have an open sigma bonding orbital, that you're going to have the two electrons available that are going to be covalently bonded together are going to be taking place in that, or are going to be taking that orbital. So, yeah. And what this does is, so does that make sense, that concept? And if you want to get really informal about it, you're basically taking the electrons on the left and right side and you're filling them up going from low to high. That's what you're doing. Ta-da. And keeping in mind Hund's rule off-bout principle, where you're filling them up. Let's say you have, for a P, you're going to fill them up like this. And then you go back and fill up the second one. Just like we've always been doing. But there's going to be more of them later on. This is the simplest molecule to understand this with. But there's going to be, to cut to the chase a little bit, there's going to be things like this. And we'll cover that in a second. But does that make sense that you're basically just, we're representing bonded molecules differently now? We're using this kind of chart. And this is called the molecular orbital theory. And you basically fill it up from low to high. Any questions? No? Okay, cool. So what this can tell us, other than paramagnetic and diamagnetic for sure, is the net bonding interaction. This word, net bonding interaction. So if you have an offset of more bonding electrons than anti-bonding, not non-bonding, anti-bonding, it's different. So if you have more bonding orbitals or more bonding electrons than anti-bonding, you're going to have a net bonding interaction. What that means is, like, you can imagine the bonding outweighs the anti-bonding, therefore the molecule is going to bond. That is exactly what happens. And you can actually calculate this number, and it's called the bond order. So the bond order basically tells you, is something possible? So is the molecule possible? Very important. I don't know why I made it bigger like that. It's important, bond order. So tells us if the molecule is possible. And in order for it to be possible, it has to have a net bonding interaction. So for example, if this bond order was 0, that molecule is impossible. So keep that in mind. So it's the difference of the bonding electrons minus the anti-bonding electrons divided by 2. That's the bond order. Okay, so we're going to use this and we're going to do some examples with it. So the hydrogen example, that's helium. So the hydrogen example, the bond order is the bonding electrons where there's 2 minus the anti-bonding where there's 0. So that's going to be 2 minus 0 is 2. Divided by 2 is going to be equal to 1. So the bond order is 1. And also, tie that into what you already know. You know that's what hydrogen looks like. That's what the hydrogen molecule looks like. Doesn't it make sense that the bond order is 1? It has 1 bond. That's it. Wow. I hope I blew your mind. Okay. Any questions on that? So that should, we're going to do examples. We'll do a lot of examples. And it'll get more complicated, but that's the primary concept. No? Okay. All right. Next is what Jabral was saying about helium. What's up with helium? So helium is just like hydrogen, but it has 1 more proton and then it has 1 more electron. So this is what the 1s orbital of helium will look like. It has 2 perfectly fine happy electrons because it's a noble gas. Take 2 of them together, try to bond them. 2 of those electrons will take the bonding orbital. The other 2 will take the anti-bonding orbital. Now let's try to figure out the bond order. 1/2 times 2 bonding minus 2 anti-bonding equals 0. Since there are as many electrons in the anti-bonding as in the bonding orbitals, there is no net, that was a bad line. There's no net bonding interaction. That means this molecule is impossible to make. I mean, in chemistry, you never want to say impossible, but this molecule will not happen naturally. So there we go. So now you can predict paramagnetic or diamagnetic using this technique, and you can predict if a molecule is possible.
I have a question.
Yes.
Can you go through the order with which the sigma bonds are filled with these 4 electrons that we have?
Yes. Good question. So I'll just draw over these. So it'll go, it's always filling up the lowest, it's always filling up the lowest one first. So it's not like 1, 2. It goes 1, 2, 3, 4. Like that. So it's the 1, 2 on the bottom, the 1, 2 on the top.
That's because it's 1s, right? So that's why there's no p that gets filled?
Right, exactly. So all the valence electrons in helium are in the s. Nothing's touching p yet.
Okay.
Okay. Now we're going to get into cases. I'm glad you mentioned that. Perfect segue to where we are doing the p orbital. So this gets weird. Now, here's how it works. Well, where's a better picture? Oh, yeah. So here's how it works for P. Now, let's say we have, and I'll talk about, these are 2 different ones. I'll talk about that in a second, why they're 2 different. But let's look at, so this is one we saw before, the one on the bottom. This is the S, and this is the P. So the one on the bottom, you just fill in your electrons for whatever you're dealing with. So all these atoms, whether they're in the P or the S, they're going to have S electrons, S valence electrons. So even carbon, right? Carbon's electrons, you have 2 valence electrons in the S and then 2 in the P. So that makes sense. And that's why you need to represent both of these. Now, for a p orbital, what is a p orbital represented by? There's a possibility for a sigma bond and a pi bond, because you can't have a double bond in a sigma orbital because there's only a place for 1 pairing of electrons. But for p electrons, you can have a double bond. You can have pi electrons and sigma electrons. So basically, this one's really confusing because you'd expect sigma to come before pi, and it does in this case. So, okay, I'll cut to the chase here. You don't need to memorize the differences between these 2. What I would expect you to do is if there's a given one of these on the exam with the molecule you're trying to bond together, you should be able to tell paramagnetic or diamagnetic and the bond order. You're not going to have to rewrite these. So the point I'm trying to make is, you see how both of these are different? These both for the p orbitals. The s orbitals are the same. They work the same for every atom or every molecule. But I hate teaching this part because it's just the way it is. For boron, carbon, and nitrogen, right? We're only talking about 2s here. So for boron, carbon, and nitrogen, the first three, this is the energetically favorable state. So the lowest orbital that you fill up is the pi orbital here, the pi subshell, the pi bond subshell. So it would go, the way you'd fill it up is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's how you'd fill it up, from low to high. This was done experimentally using quantum whatever, and that's how it was determined that the pi orbital here is the lowest energy level compared to the sigma. So that's one case. Then on the right of nitrogen in the periodic table, you have oxygen, fluorine, and neon. Oxygen, fluorine, and neon follow what you would expect because the sigma orbital, the sigma 2p, which is only one, is a single bond, is represented as the lowest energy level because it's more favorable for these ones. So you go 1, 2, then you have a double bond, or you have two pairs of electrons possible with your p orbital, with your p orbital sorry, these are all p orbitals, but your pi bond, pi electrons in your 2p orbital for this case. Then you would go 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, like that. So there you go. Boron, carbon, nitrogen follow this different scheme. Oxygen, fluorine, and neon follow this scheme. And that's due to experimental data. They determined the energy level hierarchy that way. So yeah, it's kind of weird. But once we do examples, it should make more sense. So let's do O2, and we'll use these as an example. So O2, where's my eraser? I'm going to reopen this window because the eraser is not appearing, and I want it to. So what is it, chapter 11? Okay, cool. Wait, still not there. All right, whatever. Let's I'll do this. So for oxygen, here's how so oxygen we know is paramagnetic, right? But our original molecular orbital theory or molecular orbital diagram would tell us that it's diamagnetic. So here's how we actually figured out it's paramagnetic. So let's do the O2 molecule. We'll represent it here. And we can tell the bond order. We can tell all that stuff. So oxygen has 6 valence electrons. So we can do 1, 2, 3, 4, 5, 6. So that's 2p, what's that, 4. Yeah, 2p4. And then the other oxygen is going to have, so this is going to be oxygen, this is going to be oxygen. The other oxygen is going to be the exact same thing. Fill that up, 1, 2, 3, 4. Okay, so we have 1, 2, 3, 4, 1, 2, 3, 4. We have 8, well, let's do the S first. S is easy. So you have 4 electrons, you go 1, 2, 3, 4, done. Then for P, you have 8 electrons total. So what you're going to do is 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense why I did that or how I did that? You're just basically filling them up as we normally fill up the subshells in energy level order, going from low to high. Okay, cool. So from this, we can determine the bond order and the magnetism. So we automatically see that these 2 electrons are unpaired. Therefore, O2 is paramagnetic. Then for bond order, let's do the bonding electrons minus the anti-bonding. So bonding electrons, it also counts these ones. Well, it doesn't matter because they cancel out, but we'll do, actually, no, it does matter. So yeah, we know it doesn't. It doesn't matter, but we need to count them anyway. Let's count up everything. So the bonding electrons, you'll have 2, 4, well, I'll just put the numbers here, 2, 4, and then 5, 6, 7, 8. So it's 8 total. So you're going to have 8 bonding minus the anti-bonding. You're going to have 2, 3, 4. You're going to have 4. So 8 minus 4 is 4. Divided by 2 is 2. So the bond order for O2 is 2. And look, how is the Lewis structure represented? Oh, look, a double bond. That makes sense that it's 2. Yay. Okay, so we're going to do that process for a couple other molecules, and then we're done. But is there any question on that process for this molecule, for O2? If you understood that, kind of, and like maybe you didn't understand why this is like this and why the other one's not like that, but if this is given to you, would you be able to fill it in and figure out the magnetism and bond order? If so, then you're good.
Professor?
Yes.
What are the middle, like sigma 2p? How come there's 2 of them?
You mean pi 2p?
Well, there's, yeah.
Yeah. Yeah, so the reason why for pi 2p, so a pi interaction, there could be, so in a molecule, there can be 2 possible pi bonds. So if you have like the maximum number of bonds is a triple bond, you can have only 1 possible sigma bond at all times. That's why there's only 1 box represented by your sigma. And then for pi, there's 2 possible bonds. And so each bond, we know, has 2 shared electrons. So 1 bond, 2 bond. So there's 2 sigma bonds, 4 possible shared electrons. So that's why you have 2 boxes for your pi subshells. Yeah, so think about like each half, like this chunk is a triple bond, is the electrons in a triple bond.
Okay, sure. But why are they written in a different order between
Yes.
these
So yeah, why is this in a different order than this one?
Yeah.
Yeah, because experimentally, that's what they figured out with the energy, like that. There is no explanation. There is no explanation that I try to read the paper and it's still like tough to understand.
For sure.
And just energetically, that's how they figured it out. That's, yeah. And it's not that difficult to remember. Well, you don't
So that's
need
not
to
what you're
remember
getting tested on, though, right? Is like
Yeah, no, you're not going to be tested on writing this for carbon. You're not going to have to do that. If this is given to you, be able to fill it in and determine if it's the bond order and the magnetism, whether it's paramagnetic or diamagnetic.
And di is just when it does 2.
So di is when they're all paired up. So if you see, let's say we added 2 more to this, now it would be diamagnetic. But if you have anything as even 1 electron is unpaired, the whole thing is paramagnetic.
What about just 1?
That's what I just said. If there's 1, then it'll be diamagnetic. Even if there's 1, it's paramagnetic.
But not in like not what you have written right now. If there's literally like just 1 for the 2 boxes, you're saying it's still para.
Yes.
Okay.
Okay, good questions. Okay. We did this one's oxygen already. We did that. Nitrogen. So here's how nitrogen would work. So nitrogen is on the left of oxygen, or on the left of carbon. So it's going to be a different. No, on the wait. Where's
right of carbon, left of oxygen.
Yes. Yes. So nitrogen will be this kind of scheme where the pi's come first. So that's why we have it written this way. And again, don't worry about that. But basically, you're filling it out the same way. We know nitrogen has 2s2, 2p3. If you look at the periodic table, it's the third one in on 2p. So we represent these 2p orbitals with 2 nitrogen atoms, and then we know that's a total of 6 electrons. So we do 1, 2, or we go 1, 2, like it would fill it in 1, 2, 3, 4, 5, 6. So then for the bond order, we take all of the bonding, which is 2 here, and then 6 here, right? These are all bonding orbitals. The star means anti-bonding. So it'll be 8 minus 2. So 2 is the anti-bonding, which is only found in this sigma s. So 2 equals 6 divided by 2, right? It's going to be divided by 2 equals 3. So the bond order for nitrogen is 3.
How come you divided it by 2?
Oh, I did. Yeah, I just put the divide by 2 here.
Now, how come?
Oh, because that's
it's N2?
No. That's because that's the formula for bond order. So bond order is the bonding electrons minus anti-bonding divided by 2.
Okay.
And that gives you basically how many bonds that that molecule has. So if you write N2, as we know from Lewis structures, you get N triple bond N. So the bond order is 3 because it's a triple bond.
So what exactly are you adding up?
Oh, so you're taking the BE stands for bonding electrons.
Mm-hmm.
So the ones without the star,
Okay.
there's 2, 4, 6, 8, minus the ones with the star, and there's only 2. So star minus or no star minus star divided by 2. Does that make sense?
It's just because I was gonna say, like, where's the S subshell? It's on.
Oh, it's on the bottom right here.
Yeah.
Yeah.
I'm kind of never mind. Because I was gonna say, where do the if you're combining together 4 electrons, where do the other 2 go? But they're like non-bonding.
Yeah, they're anti-bonding. They're here.
Okay.
Yeah. Okay. Yeah, it is kind of tough. It's good that you're asking questions.
Not that they're not gonna bond. It just means that they're like repelling.
Yeah, they're creating a destructive interference, and
Right.
they're not favorable to bond. Yeah. Okay. Good. All right. So we did that already. Sometimes you might have a free one. That's cool. So yeah, we'll do this example. Bond order. So the bond order of carbon monoxide. So far we've done what do you call homonuclear. That means 2 atoms that are the same element. So like O2, H2, helium-2, N2. But you can also do this with atoms that are not the same. So, but the energy, it'll be a little bit different. It'll look the same, but it'll be like kind of like this. So you do the same thing. So this is going to be carbon. This is going to be oxygen, and you fill them in. Carbon is 2p2, so you have 1, 2 there, and then your S's are going to be filled up, and then oxygen is 2p4. So then 4 electrons here plus the 2 here are going to be 6, and you fill in 1, 2, 3, 4, 5, 6, and then you can calculate the bond order. So the bond order is going to be the bonding, which is going to be going from the S. Bonding is going to be 2, 4, 6, 8, 8, minus the anti-bonding, which is just going to be 2, 2 divided by 2. That's going to be 3. So the bond order for carbon monoxide is 3. And if you look at the structure for carbon monoxide, the Lewis structure, it's going to look like this. That's what it looks like. So the bond order is 3 because it's triple bond. Okay, cool. Then you can do this for other molecules like HF, and it still works. Yeah. That's basically it. Yeah, okay, cool. So any questions on that? And here's some videos too. So Vesper, all the shapes, hybridization, and we'll put molecular orbital theory. That's a video on that. So yeah, if you want extra practice or extra review, you can study from those videos. Okay, so now we are going to move on to chapter 12 very briefly. Well, chapter 12 will go through a little bit more in depth than the other ones, but 13 and 14 are not that long. So chapter 12. Well, first, are there any questions or anything? Or why did I say chapter 11? This was the old textbook, not chapter 12. Okay, so now we're going to learn about intermolecular forces. So this is important for the final. And and it's not too difficult. So intermolecular forces, what the hell does that mean? So there are two types of forces. There's intramolecular and an intermolecular. So everything that we did so far in valence bond theory, valence orbital, whatever, all that stuff, that was intramolecular bonding. So I'm going to write that definition on top. Intramolecular. Everything we've done in this class so far was intramolecular. What that means is bonding within molecules or within molecule. So if you have, that's an intramolecular bond. If you have calcium sulfide, that's an intramolecular bond. So an intramolecular bond is covalent or ionic. And those are the strongest. So, I mean, these are different types. These are ranking the strongest, weakest. That's ranking the intermolecular bonds, not intramolecular. So leave that for a second. We'll cover that in a minute. So intramolecular is what we've done so far in the class, and that is basically covalent, ionic, are intramolecular. Then there are these type of bonds called intermolecular. Intermolecular are in between molecules, in between molecules. So this is the representation of mixtures, of liquids, of why things are viscous, because they have strong intermolecular forces. Why is water the way water is? Why does water have a high surface tension? Because it has strong intermolecular forces, because it has hydrogen bonds. It forms a dipole, stuff like that. So here are the main four types, and it's always disputed in every textbook how many types of intermolecular forces there are, but I like to think there is four major types. There's dipole-dipole interactions, which are probably the most prevalent, which basically means we've talked about the word dipole, and that means, oh, if something's polar. Yeah, basically. So if you have two polar molecules next to each other, they're going to have some kind of interaction. This is called a dipole-dipole interaction because you have two things or more, could be more, that have positive and negative poles. Even if you have, let's say, we'll use this carbon monoxide example. Carbon monoxide is kind of polar, right? It's got a carbon is less electronegative than oxygen, so it's going to be kind of polar. If you have two carbon monoxide molecules together, this is going to be partial negative, partial positive, partial positive, partial negative. You're going to have some kind of interaction between the positive and the negative poles of each of the molecules. Therefore, this is what we call a dipole-dipole interaction. So that is one major type, is dipole-dipole. And the hydrogen bond is a type of dipole-dipole that is so much stronger than the other ones, we consider it its own category. But it's the same principle. It's just a stronger form of dipole. Then, and we're going to cover each one of these more in depth. There's slides on each one, but just to tell you the names. Then there is London dispersion forces, which are the weakest, otherwise known as van der Waals forces. And what that means, and they weren't invented in London. The guy's last name was London. So I thought it was made in London, but it wasn't, or discovered in London. But so London dispersion forces are the weakest. And this one is represented by when non-polar molecules interact with each other. And you can think, oh, wait, don't non-polar molecules not interact with each other? Well, they might for a little bit. That's why these are the weakest interactions. They're very weak. But let's say we have O2, have a collision, have a physical collision with another O2 molecule. That might cause some different things. That might cause some electron imbalances to go on. And I'll explain that more in depth once we talk about London dispersion forces. But basically, it's a very transient, weak interaction that happens for a split second in between nonpolar molecules, and is actually the most, I said dipole is the most common, but London dispersion is the most common force on the planet. It happens between everything. Every gas molecule is going through London dispersion, and it's very, very weak. So that's one thing. Then you have ion dipole, which means it's basically the same concept as a dipole, but you have one polar molecule interacting with an ion. So let's say you have, but this is a molecular ion, not a single ion like a Ca2+. That's a atomic ion. There could be molecular ions, such as any polyatomic, right? Any polyatomic ion, CO3 2-, that is a molecular ion. If you have a molecular ion and you have a polar molecule that's a dipole, they can create some kind of interaction. The ion represents a real charge. It has a real plus or minus. The dipole has this partial plus or minus. They can totally interact with each other because the plus or minuses are still real, and they can still form up as the pluses have a contact with the minuses and so forth. Then you can have the strongest interaction, which is two molecular ions, because the ionic force is very strong. So you have two molecular ions form a intermolecular force, and it'll be the strongest. So you don't really see this in general chemistry, honestly. So I'm not gonna mention. It's my favorite because it's, when we're dealing with drug discovery, it's the most important one. So if you have an ion-ion interaction, let's say an amino acid residue of your protein that you're trying to bind a drug to has a plus charge, and you have a drug that you made that has a negative charge that binds to it, that's going to be a very favorable, strong interaction. It's not going to be an ionic bond. It's going to be an ionic interaction, which is the strongest. But for Gen Chem, not the most important one. I digress. Okay, so let's go in detail about all of these different types. So dipole is the first one, where you have we have two molecules that are both polar, and they both have poles. They're both permanent dipoles, meaning they're polar, whatever. We know what polar is. And they have, which is true for all polar molecules, a partial minus and a partial positive charge. So they align, once they interact with each other and get in close proximity, they would align where the minus charges line up with the plus charges. So this is some kind of, this is oxygen here. This is carbon-carbon. Is a 3-carbon chain. This is I think this is formaldehyde. Yeah, it's formaldehyde. No, it's formaldehyde. No, yes, it is. It's formaldehyde. So this formaldehyde is polar, and it has a partial minus of the oxygen, and then the partial positive of the carbons and hydrogens here, the nonpolar, or not nonpolar, of the positive end, will create an interaction. That is a dipole-dipole. So that's it. Any questions on that? On dipole-dipole? I heard someone say something. Yes or no? No? Okay. All right. Now, the same concept applies to hydrogen bonding, but the magnitude of strength is a lot larger. And this only occurs with very with very polar molecules, such as water. So you've probably heard of hydrogen bonds being associated with water, and this is true. And here's what happens. So here's one water molecule. Here's another water molecule. Now, water is very polar, and all the electrons are going towards the oxygen, making partial positives on the hydrogen, partial negative on the oxygen. And what will happen in water is they will arrange in such a way where the positives line with the negatives and make that strong dipole-dipole force, which is known as our hydrogen bond. And for hydrogen bonds, this can only occur between atoms with molecules with these atoms: oxygen, nitrogen, and fluorine. That's the only way hydrogen bonds could occur. If you have one molecule with either oxygen, nitrogen, or fluorine with a hydrogen attached to it, and another molecule with oxygen, nitrogen, or fluorine with a hydrogen attached to it. Because that is the only way for this polar, or for this unequal distribution of electrons between your more electronegative and your less electronegative atom to be large enough to create a very strong force, which is a hydrogen bond, only with these three atoms: oxygen, nitrogen, and fluorine. So yeah, they're just like dipole-dipole, just a lot stronger than normal ones. All right, any questions on that? And here's a representation of hydrogen bonds with hydrofluoric acid. Same thing with water. You see how the positive hydrogens align with the negative oxygens. All right, cool. So don't worry about that. Then you have the weakest is London dispersion forces, which is what we call a temporary dipole or a transient dipole. And it's usually initiated by a physical collision between non-polar molecules and occurs for a couple seconds, or not even a second. So these are non-polar molecules. So think of both of these non-polar molecules as snow globes. You know, like you shake the snow globe and there's like snow, right? Think of the snow in the snow globe as electrons. If you hit these two snow globes together, assuming they don't break, what will happen is the snow will get excited, will get moved and displaced. That's what happens. If you hit them together, the electrons from element, or we'll call this one molecule A, molecule B, the electrons from molecule B will go towards the back of the atom, or go towards one side of the molecule, or in this case, the other, or here. That's not the way this is representing it. Doesn't matter which way, but here, the molecule, once these hit together, the electrons from A will move because of the momentum, will move to the back or the other side of the molecule. What this does is it creates a temporary negative charge, a temporary partial charge, or a temporary dipole in molecule A. What that does is, because it's in close proximity to molecule B, and one side of molecule A is minus and the other one is plus, it will orient molecule B in such a way that the electrons from molecule B will come closer to the surface, or come closer to the positive, will come closer to the partial positive of molecule A, because of the transient or temporary dipole that was established by the physical contact of the two molecules. And that will create this temporary dipole. But this interaction is so weak that over the course of a couple seconds, a second, even less, the electrons that are originally pushed to one side will come back towards the middle. And then that will regulate everything, and you'll be back to both of your non-polar molecules. And everything, and they won't interact anymore. So that's a London dispersion force. It's temporary, and it occurs because of this because of the physical contact displacing electrons for a short period of time. Now, questions on the exam you'd expect to do. If I give you, or if the test, or if my boss gives you, what type of molecular force or intermolecular force is water going to have? And you, dipole-dipole or hydrogen bond. Hydrogen bond's the best answer. What kind of intermolecular bonds would you expect with F2 molecules? So F2 is nonpolar, right? So you'd expect London dispersion. What about What about formaldehyde? Oh, it's kind of polar. So I would expect dipole, dipole. What about NF3? Oh, dipole, dipole. What about NH3? Oh, they're probably hydrogen bonds because it's one of the ones that hydrogen is either bonded with nitrogen, oxygen, or fluorine. It will create hydrogen bonds. So things like that is giving you molecules and which bond would it do? Or the opposite, giving you a bond and then giving you a choice of molecules. Which molecule is most likely to partake in dipole-dipole, for example. So things like that I would expect you to do. Okay, we talked about dispersion forces.
Professor?
Yes.
We go back to the slide you were just on?
This one? Yeah.
Like, I don't really see the difference because it's positive and negative combining. Like,
Right. So the London dispersion, it's a very temporary interaction. So keep in mind, these dipoles, the permanent ones up here, they are always like this because they're polar molecules. They always have one side of the molecule is positive, and then the negative side has all the electrons because of a difference in electronegativity. And so the electrons are unequally shared.
yeah.
So that makes this interaction. And it's stronger, and it's all the time. In the London dispersion, we deal with non-polar molecules, meaning the electrons are in the middle initially. They're
non-polar. Okay, I
non-polar,
get it.
right? And then once they hit, they become temporarily partially charged because the electrons move and then create this temporary interaction.
So what is going on with the big stuff at the bottom?
Oh, yeah, I don't know. It's different ways to represent it. Like they're saying, like, oh, if the electrons are pushed to this side, it kind of misshapes the molecule to make it like that. Not really too important. Just know this scheme I explained.
Oh yeah.
Yeah. Ignore these. Actually, I'm gonna delete them. They're stupid. Okay. Cool. Good question.
They would just need an explanation because I was trying to connect that to the dipole.
Yeah. So London dispersion is just a temporary dipole, just very quickly, and then it stopped. And another thing we call it is an induced dipole. There it is. So induced dipole.
Mm-hmm.
That means it's induced by the physical interaction or the collision of two molecules, and then it quickly goes away. Okay, so that's not really important. Oh, this stuff is important. So basically, another thing you can speculate when dealing with intermolecular forces is the boiling point of different things. So if you have larger, more complex molecules, that leaves room for more interaction. And if you have more intricate shapes, that leads for more interactions. So basically, the larger the molecule is and the more strong interactions it has with intermolecular forces, the higher the boiling point. So, and that makes sense because if you're thinking about it, what is boiling point? Boiling point is the temperature or kinetic energy that molecules need to reach in order for them to be escaped as a gas. Now, for water is a relatively high boiling point compared to methane or methanol or things like that because it has pretty strong intermolecular forces. Water is held pretty tightly together by hydrogen bonds. Because of that, the boiling point is high because it requires a lot of energy to, one, break those hydrogen bonds, and then to give the molecules enough kinetic energy to escape as a gas. So you have to break those intermolecular forces. You need enough energy to do that and to give them kinetic energy to escape. So it does require a lot of energy. Things like ethanol and methanol have lower boiling points here's ethane. Here's methane and ethane. Boiling point's very low, extremely low, because there's not really many, these are basically nonpolar, all of these. So they don't really require that many, they don't really have that many intermolecular forces to break. So the boiling point's going to be low. But you can see as the size increases and as the intermolecular forces increase, the boiling point and melting point increase as well. So that's an important thing to just know, that you might get a question, which one of these has a higher boiling point? And the answer is, it's all based on intermolecular forces. Whichever one creates the strongest and most intermolecular forces will have the highest boiling point. So keep that in mind. And then I think that's it for the important stuff of chapter 12. Liquids, not really go about that. Boiling point. Vapor pressure. I don't think this is going to be on it. Well, it's not. So we know about intermolecular forces. So we should go over phase diagrams. So we'll just go over, let's look at the curve. So here's a phase diagram. So kind of talks about boiling point a little bit, but really it represents the phase transitions going from solid to liquid to gas. And we've covered the simple one, I think, in the first day of class, where if we heat a solid, it'll go to a liquid, then it'll go to a gas, and then the temperature will just keep increasing and go on. And I think that was, where was that? Here, this one. So we went over this kind of thing already a while ago, but you know the phase transition from solid to liquid to gas. As you increase the energy, you also increase the temperature, increase the speed. So those are all related. Another thing that's related to state is the pressure. And we will, so I keep flipping through slides, but we'll go here. So for pressure, you don't even need temperature. You don't even need a lot of temperature or high temperature to make something a gas or a solid, or a low temperature to make something a solid. All you need to do is change the pressure. So whenever we say boiling point, whenever we say melting point, we assume atmospheric pressure of 760 torr, 1 atm, whatever you want to call it. Now, if you were on the moon or if you were in space, it would be a lot different. The pressures would be different, and then your boiling and melting points would be different. And this is because of intermolecular forces, and also pressure is the force applied to a substance. Now, if you have a higher force applied to a substance, you could imagine it's more difficult to break apart into a liquid, into a gas. And it's more difficult to speed up those molecules. So that's exactly true. Now, we talked about water. Water's a little bit different. But for most molecules, if you compress them, let's say a liquid, let's say you have methanol, right? Liquid. Or, I don't know, ethanol, because it's like drinking alcohol, whatever, moonshine. You put that under extreme pressure, you will turn it into a solid. At room temperature, doesn't matter what temperature. If you put extreme hundreds of ATM on a liquid and compress it, you will actually form a solid. You will force the molecules based on pressure alone to become a solid. If you decrease the pressure, it'll become a gas. So it's a common thing in organic chemistry to do what we call vacuum distillation. We decrease the pressure a lot in order to decrease the boiling point. So let's say you have an organic substance that has a temperature or a boiling point of 250 degrees Celsius. Our Bunsen burners don't go up that high. That's incredibly hot. And it might take a while. We put a vacuum in there, that boiling point goes down to 100 or even 60 degrees. And we don't even need much heat to boil it. So pressure has a strong effect on when you're going to boil and heat and melt. So the way we can represent that by these phase diagrams, which on the right hand y-axis you have pressure, and on the left hand, or going left, you have the x-axis, which represents temperature. So you can see how if you increase pressure, how the boiling point changes based on these lines. So let's say here's the vaporization curve, right? Basically boiling point. So if you have a pressure of 760 torr, which is 1 atm, your boiling point is 100 degrees. If you have a higher pressure, your boiling point is higher. Let's say if it's 800, it's probably around 110. because you're going to need more energy to overcome the forces put on you by the increased pressure. Does that concept make sense? If not, you could watch this when I put it on YouTube, but or you ask questions. But so yeah, so basically I'll say it one more time. The pressure, once the pressure increases, more heat and more energy is required to be put into the substance to overcome that pressure and turn it into a gas. And then the opposite applies for sublimation or for fusion or whatever, from changing it to a solid to a gas or whatever. So let's say here's the melting point, right? So here's 0 degrees, the melting point of water. So this fusion curve, this one right here, represents the melting point. If you increase the pressure all the way up here, it decreases the melting point a little bit. So that's because you're decreasing the force that's be put on the liquid. So that means less heat is required to bring it from a solid to a liquid, because you're kind of giving it room to breathe. You're not putting as much force on the solid, so then it would take less energy for it to become a liquid. So that's the same thing. That's the same concept, but just the opposite direction. So I hope that makes sense. Now, there's certain things on this phase diagram that are important to mention. The triple point. So the triple point is where the curves for the melting, the boiling, and the sublimation, they meet. And basically, there's a temperature at the triple point and a pressure there'll be a mixture of all three, solid, liquid, and gas. And that's probably for water, if this is accurate. Well, it says not to scale, but it would be probably less than 760 around here, and then a little bit higher than 0. So that'll be the triple point. And then there's a critical point. So the critical point is where above that, any higher pressure or temperature, you have what we call a supercritical fluid. Now, supercritical fluids are not really understood too much, but we have a definition here. Yeah. That's where you...
It was right there. Go like forward or back one.
Yes, supercritical fluid. Okay, so how's a good way to explain this? So it basically is like a gas and so it's a liquid, but it has a pressure to it. It's kind of like a liquid and a gas put together. There's no meniscus. It's just kind of like it wouldn't be a normal liquid. It would be liquid at a very high temperature, but because the pressure is keeping it in check, it won't turn to a gas. So as we call it, like a supercritical fluid. So it's kind of like the vapor and the liquid state kind of mix together, and it creates this intricate substance called a supercritical fluid. That's only at extremely high temperatures and extremely high pressures. So yeah. Yeah, so the gas cannot be condensed into a liquid. So no matter what your pressure is, your gas cannot be condensed. That's how high the temperature has to be. So it's very rare. You don't really, there's research done on it, but you need like high-tech stuff to do it, extremely high pressures and temperatures. But yeah, so that's basically it for chapter, it's the same thing for carbon dioxide. So that's basically it for chapter 12. So is there any questions on that? On this concept of the phase diagram or the intermolecular forces? Those are the main things: phase diagram, intermolecular forces. All right. If not, then I will go to chapter 13. The 13 structures, solids, and stuff. So we talked about lattice. This is not going to be that long, and chapter 14 is not that long either. So lattices. We talked about crystal lattices, meaning the lattice energy, lattice structure, that it's basically a unit of representation of an ionic solid. And it really doesn't have to be an ionic solid. It can be any solid, basically, that has small units that repeat. So it's basically the breaking down the three-dimensional structure of a crystal, just like this one, into its atomic form and seeing how they form. And there are different ways of representing them. There are different ways of the different types of lattices, and they're called unit cells. So a unit cell is a subsection, kind of like if you take an entire molecule of this crystal, and you take a small subsection that's a couple of atoms thick, right? Then you'll create a unit cell. So it's basically one unit represented. And you basically take multiple unit cells and you put them together, billions of them, and you get your crystal. So what you can do, I mean, there's X-ray crystallography. We're not going to cover that. That's not, Bragg's law is more for physics. Not really important. But what is important is the cubics, the different types of unit cells. So the solids can form 3 different types of unit cells. And you can figure out from the unit cell type the volume of it and the density and stuff like that. But basically, the first one is called a simple cubic. Well, I have a chart. There it is. So this chart is really the only important thing that's going to be on the test for, ignore the band gap theory, all that stuff. But this is the only important thing. So you have simple cubic. So this is represented by, I need a sphere. Here we go. Actually, I should have started here. Yes. So if you have a bunch of atoms that are in this lattice, and you took that unit cell subsection, this might be difficult for you to see, but basically, this is one way of representing the lattice. And if you want to calculate how many atoms are in a simple cubic, that's something that's important to know. So in a simple cubic, this is what it looks like, this picture to the right, where you have, it looks like 1/8 of a little subsection of an atom is cut off by each corner. And this is what the lattice looks like. So what you can say is each corner is 1/8 of an atom. There are 8 corners to this cube. Therefore, each simple cubic represents 1 atom. And that's exactly true. Also, knowing what type of atom it is, you could determine a lot of things. You could determine density, you can determine the volume, and a lot of things based on the atomic radius. So this is lined up perfectly, in which you see that the atomic radius of this atom would be, there would be 2 radii here. They'd be along the edges. So you would do the radius times 2, and that number times, or that number to the 3rd to get the volume of this simple cubic. You can figure out the volume that way based on the mass of the atom, based on basically what element it is. You can divide that by the volume and figure out the density of the cubic, or a mole of cubics, or whatever the case may be. You can figure out a lot from it. So a simple cubic is 1 atom because it's like this. Then you have, and then the edge of it is 2 times the radius of the atom that it is, based on what I said. And then you can do that to the 3rd, which will give you the volume. Then there's the second type, which is called a body-centered cubic. So body-centered cubic has a little bit different arrangement, but here it is. And you can tell, we can calculate the same thing. How many atoms are in each cell? So the way the cubic, or the unit cell works, there's 1 atom in the middle as a whole, and then you have the 4/8 on the top and the 4/8 on the bottom. So you add all those up and you get 2 atoms per cell. So a body-centered cubic equals 2 atoms per cell. And that's why they call it body-centered. There's 1 entire body in the middle, and everything else is cut off. So same thing applies for there. And the edge of it is a little bit more complicated, and they have this equation for it. It's the length of the edge equals 4 times the radius of the atom divided by the square root of 3. So you can tell it's like, oh, it's a little bit more than 2 times the radius. There's a little bit more to that. So they come up with the equation 4r over the square root of 3. And someone's thinking right now, I can tell, Oh, do we need to memorize these equations? No, you don't. So that's good. But you should memorize how many atoms are in either the simple cubic, the body-centered cubic, and then the next one, which is the face-centered cubic, which has the most atoms. So body-centered, meaning there's a body in the middle. Face-centered, which kind of means, I shouldn't be face-centered. It should be face-edged or something, which means there's faces, like, of the atom. Like, here's a face right here. That are on the side, that are on the edges. So let me pull a funny real quick. You know what I'm gonna do? I'm gonna draw a face on it. I think I do this every year. Nope. Wait. There we go. There we go. So it's a face and the C is the node. That's perfect. So yeah, there is a face-centered cubic. So how many atoms are in it? You have one, there's two in the back. These are halves. There's 1/2, 2/2, 3/2 over there, 4/2 at the bottom, 5, 6. 6 halves, that's 3. And then you have the 1/8 on the side, and that's 1. So 3 plus 1 equals 4. So yeah, that is the face-centered cubic. And then the equation for the length is a little bit more difficult. You have the 2r times the square root of 2. Again, you don't have to memorize that. And if you were to have it on a test and you were to ask for the volume, you take that and you take it to the third power. Okay, so here is a question. Now, here's something you might expect. So calculate the density of aluminum if it crystallizes in a face-centered cubic, FCC, and has a radius of 143 picometers. So meters, I mean, they convert it to centimeters if you want to find density in grams per centimeter cubed. And then the mass of it is 1 gram per mole. So you know that information. So first, how many atoms are in the unit cell? A face-centered cubic, we just did, there's 4. There's 4 atoms. Then figure out the mass of 1 atom of aluminum. So basically, 226.98 divided by Avogadro's number. So that's grams divided by Avogadro's number. And that equals something really small. 10 to the 23rd grams. That's going to be very, very, or grams per mole. Or no, moles per atom. Or no, molecules, shit. Atoms per mole. Atoms per mole. So you divide that, you get a really, really small number. Multiply that number by 4. That equals the mass of the unit cell. Then you know the length of the unit cell by the equation and by using this. Then you determine the volume, then the density by doing the mass divided by density, or mass divided by volume. So we'll walk through the work real quick. So you know that the face-centered cubic is 4 atoms per cubic unit cube. We know that the mass of 1 atom of aluminum is 1.79, or sorry, of 4 atoms of aluminum, because 4 atoms are in 1 face-centered cube. The mass of 4 atoms is 1.792 times 10 to the negative 22nd grams. Then the length of it is going to be, you take the picometers, the radius, and you convert it to centimeters, and then you use the edge length equation to put that centimeters in there, and you come up with the 2 radius times the square root of 2. You come up with 4.05 times 10 to the negative 8 centimeters, and then you do your grams divided by your centimeters, and you figure out the density. That's 2.71 grams per cubic centimeter. So yeah, I know I went through that kind of whatever, but there's the work. Would you be able to do something like that? And if not, please ask a question about it. If you were given the edge equation and you were being given, like, find the density in grams per cubic centimeter. You don't assume it's grams per cubic centimeter. You're going to be, the answers might be in grams per cubic centimeter. So you'll have to convert to that. Okay. All right. So in summary, there's 3 types. Simple cubic, which has 1 atom. Body-centered, which has 2. Face-centered, which has 4. Know each type, the atoms in each unit cell to determine the mass. Relate the length of the cubic to the radius of the atom. So the equations, but you don't need to know those, but they'll be given. And then you can use all that information to compute the density. So there you go. Okay, so that's basically it for chapter 13. Any questions on that? No? Okay. Next is chapter 14. And I don't know why that, so we're going to learn, we learned some of this stuff already. But it's just, really it's just a couple of, it's just plug and chug, honestly, but we're going to go over it. So solutions. We understand already how solutions work, where you have a solute, you have a solvent, and they mix together, and based on the type, if it's a non-electrolyte, a weak electrolyte, a strong electrolyte, they have to, they interact differently. So NaCl, we know that it's ionic, right? It's a strong electrolyte. So the positive sodium is going to interact with the negative of the water, of the oxygen, and the waters are going to kind of attack the sodium molecule, the sodium ion. And then the waters are also going to attack the chlorine and thus ripping up the sodium chloride molecule into its ionic components. So that's how mixing works. And we know for non-electrolytes, the water kind of attacks it also based on its charge, its partial charges, but doesn't rip it apart. Now, solubility. You can have substances that are insoluble and substances that are soluble. How do we determine if something is soluble in something else? To cut to the chase, it is based on the intermolecular attractions. So, oh no, intermolecular forces are back. But basically how it works is if you have the same intermolecular force type, you are going to mix together. Meaning, likes dissolve likes. So polar dissolves polar, while nonpolar dissolves nonpolar. Very easy, right? So if you have water, that's why water doesn't dissolve in oil, and oil and water don't mix. Oil is nonpolar. Water is polar. So there's not going to be any intermolecular forces that are going to be miscible in each other. So that's that word, miscible. 2 liquids that are mutually soluble, are said to be miscible. Alcohol and water are pretty miscible. Oil and water are immiscible because they have different intermolecular forces, and something that only partakes in dispersion forces is not going to have a strong interaction or an interaction at all with a dipole, such as water, or a hydrogen bond, such as water. So dipole, and hydrogen bonds and ion dipoles, they are all polar. They will all interact with each other. But nonpolar molecules that partake in dispersion forces are not miscible or immiscible in polar solvents or solutes. So likes dissolve likes, dislikes do not dissolve dislikes. All right. What's next? Is there any questions on that concept? Questions you might receive are like, which of the following dissolves in methane? And we know, oh, methane, CH4. It's pretty nonpolar. So, and another thing is, if you're unsure if the molecule is nonpolar or not, write the Lewis structure. Know the shape of it. All that stuff we did previously will help you for this. So hopefully you're seeing that, like, we know what we went into depth about bonds today, but like everything is coming together. That you can determine if you're given methane, you know so much about methane, CH4, all right? I'll write the Lewis structure. I'll calculate the molar mass. I can tell about its intermolecular forces. I know about its bond hybridization. I can do all this different stuff. I can tell which substances it's soluble in. I can tell it's cubic, and not really cubic, but I can tell, I can relate, I can relate its boiling point to another substance. Is its boiling point higher than propane? No, it's not. Why? Because its intermolecular forces are less and it's smaller. Things like that. So it's like, just from saying a formula, you should have all these ideas about what these different molecules behave like. So yeah, it's kind of coming together, or at least I hope it is. Concentrations. So the last thing for chapter 14 is concentrations. Now, I don't know why we wait until the end. Molarity is a crucial part of Gen Chem. And it's usually in most textbooks, it's taught towards the middle where we're learning about stoichiometry. So molarity basically is one way of determining the concentration of chemistry. It's the most common one used. And the unit is the moles of a solute divided by the liters of the solution. And it's represented by big M. So you can have I'll just write it then. Oh, wait, what am I doing? So you can have a 2 molar, so 2M HCl. That's pretty concentrated. That means you have 2 moles of HCl per liter of that solution, per liter of water. That's pretty concentrated. But you can have different types of molarities. So yeah, I think we kind of touched upon concentration already with we did dilutions already, I think. So yeah. That's one unit of concentration. And in terms of math that I expect you to do, basically plug and chug. If you have grams of a substance, you can easily convert that to moles, divide it by the liters, and then you get your molarity. There's another one that's mostly used in chemical plants for large batches, is molality. So it kind of sounds like if you have a lisp and say molarity, molality. So it's a little bit different. It's a small m, and it's represented by the moles of solute, so that's the same, but divided by kilograms of solvent. So the only time that the molality is equal to the molarity, well, technically they're not ever equal, because molarity is liters of solution, whereas molality is kilograms of just the solvent. But they would be similar if you have water, which we know that 1 liter of water weighs 1 kilogram. So that would be about the same. But if it's not water, then it'll be a lot different. So molality, that's another one. So moles divided by kilograms of solvent. So that's a good one. It's based on masses and not volume. So that's why it's used in chemical plants where we're dealing with a lot of heating and stuff, things boiling out of solutions all the time. Molarity will always change. The molality will not change because the mass of the solvent will stay constant. All right, so mass percentage. So this one's not too bad. I mean, you should have an idea of this one already. So mass percentage, you basically take the mass of your solute divided by the mass of the solution times 100, and you get the mass percentage. Volume percentage, same thing. So yeah, is there any more explanation I need to do on that? If so, please ask the question. I feel like I'm breezing over this, but I feel like we've done things like this in the past. No? Okay. Then mole fraction, where we definitely covered in gases, where you have the moles of one component over the total moles of your mixture. So so we've done that before. So it's out of 100, and it's just a fraction. So it's out of 1, sorry. Then you have this one. This we haven't covered. So this is the last thing. Colligative properties. So basically, there are 3 colligative properties. What a colligative property is, it's a property whose value depends on the number of solute particles and not what they are. All right. So basically, what that means is freezing point, boiling point, and there's another one, osmotic pressure. We're not really going to worry about vapor pressure, vapor point depression. We're not going to worry about that one. Vapor pressure depression. But the main 3, which is freezing point depression, boiling point elevation, and osmotic pressure, the number of, let's say, ions you have, or a number of molecules in a substance does change its boiling point a little bit. Why? Because increased intermolecular forces. If you have more concentrated HCl, that means the boiling point will be different than less concentrated HCl, because you have less HCl, which means there's less intermolecular forces, which means it'll boil at a different pressure, a different temperature. Same thing for freezing point. So based on the number of particles and the strength, or not really strength, but the number of intermolecular forces, the freezing point and the boiling point do change. Is there a question, or that was just, oh, it's okay. Okay, so based on the number of particles, that changes. Same with osmotic pressure, which just means the pressure that water can flow into and out of the mixture based on the number of other particles there. So for freezing point, depression, and for all these things, there are very simple equations. So the change in freezing point here, delta TF equals M, which is the molality. So the molality of that substance times KF, which is a depression constant that depends on whatever solvent you're using. So again, I'm going to be throwing out, there's 3 equations here. I know it's towards the end of class, but they will be given to you when you need them. And I have to look at the final before. I'm going to send her an email after this, because I'm like stressing out, because I'm like I'm assuming they'll be given, but if they aren't given, I will give it to you, because I'm saying they're given. So, oh, okay. Sorry, I got a message. Okay. So freezing point, depression, very similar equation to the next one, boiling point, elevation. Actually, they're all really similar. But basically, let's say you have water, right? And where's water? Here's water. So a normal freezing point of water is 0. The KF value is 1.86. And let's say you have whatever molality of whatever something in water. So what is going to be, a question would be, let's say you have NaCl solution, a 2 molar or 2 molal solution of water, or in water. Sorry, hold on. I'm going to get my pen so we can do this. All right, so we have a 2 molality solution. So 2 moles per 1 kilogram of H2O, and there's going to be 2 moles of NaCl. What is the freezing point of this solution? So what you would do is, KF for water is 1.86. So what you would do is you take your molality, 2 times your KF, which is 1.86, and that would equal a number. Of course, it would equal a number. Let's see which number. 1.86 times 2, 3.72. 3.72. All right, so 3.72. This is the change in freezing point. What this means is that the freezing point of water, which is 0, now increases by 3.72. So now the new freezing point of water is 3.72. Not because delta TF was 3.72, because it increased that much. Or sorry, decreased, depression, my bad, decreased. Minus. So now it's negative 3.72. So if you have a different substance that's not water, and let's say the freezing point is 60, you do 60 minus 3.72, which will give you your new freezing point. So just because you solve the equation doesn't mean that's the final answer, is what I'm trying to say. So does that make sense?
Yeah.
Okay, cool. So then you have different freezing point values for different substances. I mean, you don't have to memorize any of this, but you'll be given it as you need it. And the same thing applies for boiling point elevation. Exactly the same concept. So where you have a KB this time. So that's a boiling point constant, which is right here. and that's boiling point elevation. So if you're confused about which way it goes, like I just was, you just look at the name of it. Freezing point depression. Oh, decrease. Boiling point elevation. Oh, increase. So that should, yeah. Then osmotic pressure. So osmosis is the flow of the solvent, so of water usually, through a semi-permeable membrane to equilibrate the pressures. So going from a high pressure to a low pressure. And the osmotic pressure directly relates to the molarity of the substance. So that makes sense because it's going from high concentration to low concentration and or pressure. But in this case, we're talking about concentrations. So it goes from high concentration to low concentration. So in this case, the molarity determines the osmotic pressure. The higher the molarity means the higher the pressure of osmosis to be added or removed from that vessel. So if you have a high molarity, a high concentration, there's going to be a lot of pressure to relieve that high concentration with the rest of the mixture, with another part of the mixture if you have a semi-permeable membrane. So let's say, like, we'll give a better example. So let's say you have this thing, this tube, right? In the middle is a semi-permeable membrane. Here you have a high concentration. Here you have a low concentration. If you have an extremely high concentration here, what's going to happen is there's going to be so much pressure for the solvent of this side to move to the left. Because, like, we need to relieve that pressure. There's so much concentration there. We want our concentrations to be equal. So we want to go from high concentration. Well, we want the solvent to move. Well, in this case, the solvent's not going to, the solute is not going to move. So one of two things can happen. Osmosis, the solvent will flow from the low concentration area to the high. And what that would do is it would make this concentration lower, and they would eventually be equal. Or the solute could move from high concentration to low, and that would make it also equal. So one of those pressures is going to be really high if there's a big offset, and that's what makes the osmotic pressure high. And it's also based on the R constant. Oh, look, it's back. The 0.8206 and the temperature in Kelvin. Because you can imagine as you increase temperature, you're going to increase pressure as well, because this is a closed vessel, just like we've talked about for gases. So yeah, Van Hoff factor, don't really worry about Van Hoff factor, Rayleigh law, whatever. So yeah, there you go. That's it. Ta-da, we're done. So just to reiterate for Monday, or is there any questions? Any questions on anything? Here's some more YouTube videos at the end. All right, so we're almost done. We're done with everything. Oh, wrong button. So just to reiterate again, for those of you who weren't here in the beginning of class, final exam, you will be, or before, actually, I would say do it today. Do it. Check it out first. Make sure your lockdown browser works. Do everything early, because you don't want the day of the final for you to be freaking out and you can't get on, because everything's timed. It starts at 9 o'clock. It ends at whatever time it ends. So you want to be and you don't want to be scrambling. So after class, whenever, click lockdown browser, download it. Use one NJIT, install it. Put Moodle, log into Moodle, make sure it works on the lockdown browser. Sometimes cookies and stuff, it might not. I don't know. Make sure it works. Also here, Mac version. So do you need a Mac version? So I guess you click there, and it gives you a Mac version. I don't know. It might not even download on my Windows, but there's a Mac version if you need it. Wait, what was this? Your system, Mac OS. That's not my system. Okay, but whatever. But I know mine works. But you download it, see if it works. It's going to ask you to close down all your other applications, so do that, and then try to look at stuff through Moodle. Make sure web pages load and stuff like that, just so you know that the lockdown browser works. Then on the day of the exam, you will go into Moodle using your lockdown browser, and Where's Moodle? Moodle. All right, so then you'll go into Moodle. You'll go into your class, the class, and then you will go, under July 13th final exam, you'll see another thing pop up that says final exam, take it here. And I'm pretty sure it's not going to be like the other exams where I give you a PDF and a Word and you just complete it and submit it. It's going to be the questions and answers, kind of like the homeworks, where, I mean, it's going to be A, B, C, or D, but you're going to have to submit it online, so it grades it automatically. Because I feel bad for the TA. She's been grading very well. So 60 multiple choice questions for times 28 students, that'd be a lot. So it's done automatically. So yeah, everything should run smoothly. If you have any questions, let me know, of course, and I will give you more information about the final. I'm gonna send an email to my boss after this class, and I will ask about what if they don't have webcams, stuff like that. Oh, look, here's the due date for the homework. That's why I wasn't updated. It was April. It said April. July. What day is supposed to be due? July 14. I'll make it 14, whatever. Okay. So, and it should be at 12 or midnight. Yeah. Okay. Yeah. So, yeah, if there's no other questions, that's it. I will break you out into breakout rooms, and you can work on, I guess, chapter 11 regular homework 2, or chapter 12 homework, basic homework, or whatever. Yeah. So it's been a pleasure. This is my last time I'll get to hear from you. So yeah, it's been a pleasure. I love teaching this class. Online, it kind of sucks because it's just, it's online. I'd rather teach in person so you could see my mannerisms better. But still, I had a lot of fun. It was a learning experience for me. And I hope you learned something out of the class or gained knowledge about molecules and stuff. I should stop the recording. Let's see. Stop recording.